Hi guys, I would like to share with you this book that I bought um, from this iuniverse.com. The title of the book is Forces of Nature, and this book actually discusses about the principle of rotation. Having reading through this book, I understand that this author um, specifically is trying to explain um, rotational relativity. What actually this means is that um, it actually states the effects of a body in a rotary motion relativity. So let's begin with considering a case example of two travelers, traveler A, traveler B in a train. Now this train is moving at a speed of v, right? So from an observer outside the train, the observer can see both travelers actually in itself traveling at the speed of v, whereas for traveler A and relative to traveler B, they would consider themselves as not moving at all, which means that v equals 0 relatively. Now we go forward. What this rotational relativity is about. In one of the chapter, stated that this title of paradox of a merry-go-round. Suppose we have a merry-go-round, right? And we draw a circle here, all full circle. Okay, this is the top view, and we have a traveler A, which is close to the circumference, and then another traveler B, and traveler C at the center, or the pivot of the merry-go-round. Now among them, right? They are differentiated by a distance of x, or we can call it d then. D for distance. Now for a start, if we rotate this merry-go-round 360 degrees, right, all the three persons will come back to the same point. Here's the starting point and also the ending point. The three travelers in the merry-go-round, enclosed merry-go-round, when they look at each other, they will unknowingly know that they have actually completed a full circle. Alright, when they look at each other, all of them are at the same point, even after traveling an entire circle with a merry-go-round. But from an observer outside, B, observer, he will see that traveler A was traveling much faster than traveler B, and traveler B was traveling much faster than C. So in other words, the speed of A, traveler A, is bigger than the speed of B, whereas the speed of B is bigger than the speed of C. Now, unless the radius equals 0, the speed of C will be more than 0. Now, why is this so? This is because, say, traveler C is center, right, and we have a big circle, and C was starting point here. It was facing west. When the merry-go-round rotates through 90 degrees, traveler C was actually looking at north already. The orientation starts to change when it goes to another 90 degrees, for example, then he's looking at east already. By the time he gets here, he's looking at south. and once it's duly completed, it's back to the same uh, starting point, which is the ending point. So in fact, a the traveler C, unless its radius is is equal to 0, otherwise traveler C will be spinning by itself. Now we go back to look at this picture. So when we have uh, defined that traveler A speed, the speed of traveler A was greater than traveler B, this means that actually traveler A was accelerating, and that was the reason why he was able to complete the entire circle, you know, with a longer distance but at the same time. Okay, so when the body is undergoing acceleration, a lot of things changes. Say for example, the force changes, the kinetic force also changes. We are not looking at angular velocity, neither are we looking at anything angular. We are just simply looking at the relative effect of a body in motion, a rotary motion. Okay. So what's so big deal about this thing? Well, on the look of it, there nothing seems to be um, different or spectacular. But as we gain a closer look, um, or rather as we all explore further, we will find out things that are in more of a greater detail. Okay, what I mean by this is the first, okay, I'm going to draw a lighthouse. A lighthouse. This is a side view, okay? Side view. The lighthouse shines a light and rotate at a certain frequency, right, to travel A. Okay, and also to another travel B, which is very far away. When I say very far, I'm talking about macro systems. Say for example, we are talking about in terms of light years. Okay, this is number of light years away from a traveler, a lighthouse, and this travel B is many times number of light years away from the lighthouse. Now we are looking at the top view. top view of a lighthouse. Okay, this is the lighthouse, and this is to A, and then to B. Alright, now when the lights get shines from left to right all the way to B, and the lighthouse makes a spin of that light, and say at a certain time, right? By the time it reaches here, and by the time when traveler A sees it, there will be a time different. Why do I say that? This is because traveler B is very much further away from the lighthouse than traveler A. When the lights makes a spin, right? Traveler A will get to see traveler B faster, and by the time traveler B takes the time, he would have measured that time from travel B is greater than the time from travel A. Due to the time difference, due to the change in time difference, travel B will actually calculate that the distance that he has seen from the lighthouse was B, distance of B is equals to time times speed. The path of the lights spinning in clockwise movement, right, will actually be in the form of this. No, sorry, it's not this. It's actually this. This is not. So when the light from the lighthouse reaches traveler A and passes traveler A to this point, then traveler B will then only get to see the light from the lighthouse, which is straight. So in due respect to the time space in the universe, you can actually see lots of bending of the lights What do I mean by that? Um, the bending of the light actually was stated by Albert Einstein according to his general relativity. Let's say now we have a star here, and we have a massive planet here, right? When the lights travel that nears a planet or a massive star, it will actually cause the light to bend. Now this is a known fact, alright? This is travel A. But there's another thing that we should take note is that if such a thing can happen, what it actually means is that we could actually see a double light from a single star. Now my drawings are a little bit poor here. Perhaps I can draw in a better perspective. This is a star, right? Firstly, we get to see the light from the star by observer here, observer A, right? Now if there's a massive, say a black hole or a gigantic planet here, right, which causes the light to bend, chances are we could possibly see double or multiple lights from a same star. A better illustration would be to put another object here, massive object, and the light goes to here and goes to here. This is known as the bending of the light. Now we go back to the paradox of a merry-go-round again. Now, just now as I've said, for travel B, unless the radius is equal to 0, C will have a rotary speed. I'm not calling this angular speed. I'm trying to differentiate the idea of angular speed versus speed in relativity relative motion and relativity. Okay. Another thing to discuss here is this is a ball, and there's a string attached to it. There's a guy here holding the string. Okay, and he swings the ball clockwise. Okay, full clockwise multiple times. After swinging several times, he let go of the string and the ball will fly tangentially at the point of release. This is a known fact, but the other thing that we need to stress is that after the release, the ball will not only fly tangentially at the point of release, but the ball will actually orbits or rotates in itself while flying off. Why is this so? Reason being is because if we look at the ball from this angle, the starting point, okay, the ball was at the 9 o'clock starting point, was orientated to the 3 o'clock, which is the east. When the ball gets to the 12 o'clock, the same string was facing south. When the ball goes to the 3 o'clock, the ball was facing west. When the ball comes to 6 o'clock, it was facing north. And when the ball gets back to the starting